Um, all right, everyone. Welcome to this week's ICA seminar. We're very pleased to have Daniel Gottesman today from the University of Maryland. He hardly needs an introduction, I would suspect, but I'll nevertheless do it. So he's the Brin Family Endowed Professor in Theoretical Computer Science and co-director of QUICS at the University of Maryland, and also at the Maryland Institute for Advanced Computer Studies. He got his PhD at Caltech, then was a postdoc at Los Alamos and Microsoft Research before he went to UC Berkeley in the computer science department, where he was affiliated with the Clay Institute. And then he became a faculty member at the Brigham Institute before UMT basically snatched him. And with that, please.
Thanks. So what I'd like to talk about today is a new approach to fault-tolerant quantum computation that I'm fairly interested in. And so I'd kind of like to give you an overview of the motivation for thinking about things this way, and some of the first things that we know about this. Although there's now been a fair amount of work by a variety of people, kind of in this general direction. So what I'll be talking about today is basically drawn from two papers, one by me from a couple of years ago, and one with my student Xiaozhen Fu. So first, the context and terminology. So we kind of expect that to build a large and reliable quantum computer, that we're going to need fault tolerance, right? That the individual gates of the quantum computer will maybe be pretty accurate, but not accurate enough to run a large computation, for Shor's algorithm or simulation of a quantum system. Requires, many gates, and we just won't be able to get the error rates in the gates, physical gates, low enough to get through a whole computation without really a lot of errors occurring. So in order to do that, then to get the right answers out of these computations, we're going to need some kind of fault-tolerant protocol. And so the fault-tolerant protocol is usually built on a quantum error-correcting code. So quantum error-correcting code, it's best to describe in kind of a communication scenario or a memory scenario, where we have Alice, who has a perfect quantum computer, and Bob, who has a perfect quantum computer. But the communications channel between them, which could be just a matter of storing qubits for some amount of time, is not perfect. And so Alice will encode her qubit or qubits that she wants to send to Bob using some extra qubits. That's the quantum error correcting code. And the code is designed in such a way that if a small number of qubits go wrong during the transmission, that Bob is able to identify and correct the errors. So the problem is that that's not good enough for computation, right? Because I assume that Alice has a perfect quantum computer and that Bob has a perfect quantum computer, and we know that they don't. So what happens if the error correction procedures have errors in them? And moreover, we need to be able to perform gates on the qubits, the logical qubits stored in this error correcting code, while not losing that protection against errors at any point during the computation. So, so one of the main concerns in most fault-tolerant protocols is to avoid error propagation. So in particular, even if you have a gate that's acting properly, if there's an error on one of the qubits, the gate can spread that error to the other qubit involved in the gate. So for instance, the C0 gate can cause a bit flip error to spread from the control bit to the target qubit. And it can also cause a phase error to propagate from the target qubit back into the control qubit. So the propagation can go both ways. And why is that a problem? Well, that means that if you have a code that's designed to correct, say, one error, and you have an error, well, you're okay. But then if you do a C0 gate between two qubits in that code or some other 2-qubit gate, then that error can spread along the 2-qubit gate. And now you have two errors in the code block. And two errors you don't necessarily know how to deal with this same code. Even if you can deal with them, maybe you're less good at dealing with 2-qubit errors than with 1-qubit errors. So this is something that we have to kind of keep under control when we design fault-tolerant protocols, or at least this is the standard approach. And so one way of doing that is to use what's called transversal gates. So transversal gate will take two blocks of the code and line them up, as I've shown here, with the first qubit of the first block interacting only with the first qubit of the second block. And the second qubit interacts with this of the first block interacts with the second qubit of the second block, and so on. And what that means is that if we have an error that propagates along one of these transversal gates, that it only, even though you had two errors, they're in different blocks of the code, each of which can correct one error. And so you still have kind of your original robustness against errors. And so that is a good way to deal with error propagation. It kind of channels it into ways that are acceptable to you. Now, I guess I should say that transversal gates are not enough to build a full fault-tolerant protocol. We need some more complicated constructions. I'm not really going to talk about the details of that. Well, I'm not going to talk about that at all beyond just pointing out that we need to do that. So the main result about fault tolerance, though, is that we can do it, and in particular, that there's a threshold for fault-tolerant computation. And so the threshold says that if we can get below the threshold error rate, which is some constant value, then that means that our error correcting code is correcting errors faster than they occur. The thing is that fault tolerance adds a lot of extra qubits, a lot of extra gates, and so there's a lot more opportunities for errors to occur, but this is counterbalanced by your ability to correct errors. And so if the error rate is low, you're kind of winning. And if the error rate is high, then you're losing. The extra things that you're adding cause more errors than you can fix. But if you're below this threshold error rate, then we can use the techniques of fault tolerant to make the logical error rate arbitrarily low, and therefore we can make arbitrarily large quantum computers. So this is a theoretical result, but it's a key enabling result to actually build, experimentally viable large quantum computers, because it means that there's a constant value that's a target for the experimentalists, and if they can get below that threshold, then the software can kick in to actually take us the rest of the way to reliable quantum computation. So of course, it's important to know what the value of that threshold is. So the best protocol that we know right now is kind of an old one by Manny Nil, which, according to simulations, has an error rate of maybe about 3%, 5%, depending on the exact error model that you use. So in principle, if you get the error rate below that with the right kind of error model and the right kind of assumptions about the quantum computer, then you could build arbitrarily large quantum computers. Now, this is not a particularly practical protocol, but you can also ask, could we do better? And so as far as we know, the best upper bound on the threshold is 45% error rate. So 45% error rate means that, slightly less than 1 out of 2 gates that you do is having an error. Now that's very, very high. It's very unlikely we could actually do fault tolerance at that level. And probably that's mostly due to a limitation in our ability to prove that fault tolerance is impossible, because there's not many techniques we have to do that. But it shows you that there's, in principle, room to improve even on this nil protocol to get even higher threshold values. So the other main fact about these fault tolerance is that these fault tolerant protocols require a lot of extra qubits. So again, you can ask kind of like how many qubits are needed in realistic protocols and how many qubits are actually the limit. So the kind of we've made significant progress in recent years of reducing the overhead. So that's the ratio of physical qubits to logical qubits. And so there exist protocols now which are, for certain sizes, it can depend on the size of the computation, but for certain size computation might have, an overhead ratio of 20 physical qubits per logical qubit. That's actually a huge improvement on kind of the state of the art, say 5 years ago, where it was more like hundreds or thousands of physical qubits per logical qubit. Now, the drawback of this is that you have to make some architectural assumptions, and in particular, the ability to do long-range gates. But it's hopeful that we could bring down the overhead even further. So it's sensible to ask, well, how far in principle could we bring it down? And so in that case, we know that there is no lower bound, or rather the lower bound is number of physical qubits, just has to be greater than the number of logical qubits, but it could be arbitrarily close. Now that lower bound is a limit. That's based on kind of again, a not practical result. Is completely theoretical. It applies in the limit of many, many qubits. But again, it shows that there may still be room to improve on the overhead. So those are both things that are pretty desirable to do, right? I mean, having a very strict requirement for the error rate is hard, and that makes it hard to build quantum computers that are going to satisfy that condition and that can be scaled up to very large sizes. And even if you're dealing with 20 or 30 physical qubits per logical qubit, again, a lot better than where we were a few years ago, that still means that 5% or less of your actual qubits in the computer are actually contributing to your computation. The rest are there to protect the qubits that are doing the work. Of course, the logical qubits are not located in one specific space location; they're spread out. But the idea that you have to spend most of your work doing error correction is a little bit unsatisfying, and certainly it means that we have to build a lot bigger quantum computers to get anything that we would like to do actually done. So we'd like to do better. So one way that we could hope to do better is to come up with new fault-tolerant protocols. Now, the problem is that I think there's limited room for improvement in the existing protocols. So certainly protocols based on the surface code have been very heavily optimized already. It's probably hard to get too much more improvement out of those. Protocols based on high-rate, low-density parity check codes, I think that's much more hopeful that we could see improvements there. But I think that to really improve substantially, and we can combine these ideas with the existing codes and the existing improvements that we've had over the past few years. I think it's good to have a broader view of fault tolerance to allow more kinds of fault-tolerant protocols than we would previously have considered. So in particular, I think that a new way of thinking about fault tolerance is quite possible, and it points to just a much broader class of fault-tolerant protocols than we've had in the past. So to explain this idea, I want to kind of bring up a bunch of existing and in some cases fairly old ideas about fault tolerance and show how they kind of fit together into a new picture. So let me start with flag fault tolerance. So remember I said that what we need to do in fault tolerance is avoid error propagation. Well, it turns out that's not completely true. So, and the way we can see that is through this idea of flag fault tolerance. So if you look at the circuit on the left, so that's a way of measuring the parity of 4 qubits. So that's the sort of thing that you like to do in error correction. And the problem with this is that it's not transversal, right? There's one ancilla qubit that's interacting with 4 qubits in your code. And that means that an error in this ancilla, somewhere in the middle of the circuit, can propagate into multiple qubits of the code, which would be bad, right? Because then we'd have the code that has a 2-qubit error, for instance, which is going to be harder to correct. But flag fault tolerance says, actually, you know what? Maybe it's okay if it does propagate there, so long as we know that that's what happened. And so flag fault tolerance, as shown in the circuit on the right, and I won't go through exactly how it works, but what it does is it checks the ancilla to see if there's been an error. And it checks to make sure that to see if there's been an error at one of the points where it would cause a problem in terms of error propagation. And so if we combine the extra knowledge that we've gained from doing this check with the flag qubit, that's why it's called flag fault tolerance, with the existing information we have about the errors from the regular error correction procedure, it turns out that it's okay to have an error in the middle of the ancilla that propagates badly, because we're able to identify that error, even in the context of other possible errors that could have occurred. So that's the moral here, which is that error propagation seems bad, but it might not be bad if we know that it happened. And in particular, if we know where the error started and we know how it would have propagated, which if we know the type of error, we know how it's going to propagate, then it's okay if it propagates to multiple qubits. We can just correct it just the same way that we would correct a single qubit error if we can identify it. So that's the key, is that we have to be able to identify it. Okay, so then the next idea to bring up is the idea of code deformation. So code deformation is actually a fairly standard technique that's used to do fault-tolerant gates. And so this example that I'm showing here is a way of doing fault-tolerant gates with the surface code. So in the surface code, well, one variant of the surface code lets you encode your logical qubits as pairs of defects. And then you can move these defects around. And if you move the defects between each other and around each other, you can do logical gates. Now, how do you move them? Well, you move them by kind of rearranging the local checks you're doing, the local stabilizer generators of this code, in order to create new defects that are kind of adjacent to the old defects, and to fill in with error-correcting codes in the place where you had a defect before. And so when you do that, when you move one of these defects, formally speaking, it's actually a different code than you had before. So you started with one code, which has a particular arrangement of the defects. Then you move the defects, and you move them some more, and you move them some more. And that means that you're going through a sequence of different codes. And eventually, you go through the full sequence of different codes, and you get back to the original defect locations. So you're going back to the starting code. So what you can do is you can think of this code deformation procedure as tracing out some sort of path in the space of codes. And when you do that, then the logical gate that you've done is associated with the path that you've done. And it turns out that actually even transversal gates can be thought of in this way as well, not just things that are in topological codes. So anyway, the point here is that it's actually helpful to think about not just one code, but a whole family of codes, in this case, related codes, but still a family of them. And so once you do that, you say, well, we started with one particular code. We went through this sequence of other codes to end up back where we started. But why is the first code the special one? It was kind of arbitrary, actually. We could have stopped at some other point during this code deformation and said, actually, this is now our new code. And the other ones, the original one was just a temporary stopping point. And so some more recent work by Hastings and Ha, well, and then many others, kind of takes this idea very seriously and takes it to heart. So that's the idea of a Floquet code. So in a Floquet code, instead of having just one code that we work with most of the time and then always want to return back to it, it has a sequence of codes. And none of those codes is preferred. They're all on an equal footing. And so we can just cycle through the sequence of codes. And by doing that, you can get some advantages. So in particular, Hastings and Ha had this honeycomb code where they did something that's basically very similar to the surface code. But the surface code, in order to measure the error syndrome to find out what the errors are, you have to make 4-qubit checks. And so, the surface code kind of has 4-qubit interactions built into it. But this honeycomb code, the Floquet code that Hastings and Ha found, has only 2-qubit measurements needed. So that's a smaller, like kind of less strict requirement on what you're doing, and so that is an example of the type of advantage you might be able to get with Floquet codes. In any case, the lesson that I want you to take from this is that we don't have to have a specific code that we're always dealing with. Instead, it's fine if the code changes over time. And actually, we could go even further than this Floquet code idea. The Floquet code uses only 3 codes. I mean, the original Floquet code uses only 3 codes, and it cycles between them regularly. But we could have a much larger sequence of codes, or we could have a sequence of codes that doesn't ever get back to where it started. Okay, so next idea. So this is a result by Nickerson and Bombeen. So Nickerson and Bombeen were working for Psi-Quantum. So they were building quantum computers. I mean, Psi-Quantum is building, you know, optical quantum computers. Nickerson and Bombin were our theorists, but so they were interested in the cluster state model of computation, the measurement-based computation, quantum computation, because that's kind of a very natural fit for photonic quantum computers. And in any case, in the measurement based quantum computation, what you do is you first create a large entangled state, and then you make a sequence of single qubit measurements. And so there's results that show that you can take any quantum circuit and convert it into a measurement-based quantum computation. So it's kind of computationally equivalent to the regular quantum computation. And that's even true for fault tolerance, right? If you take a fault-tolerant quantum circuit, you get a fault-tolerant measurement-based quantum computation by this conversion procedure. And so the thing is that Nickerson and Bombin noticed that, well, when you do that, you know, if you start with a fault-tolerant circuit and you convert it in this way, then you're going to get something that has a particular pattern of measurements, where you make measurements at time 1 and then measurements at time 2, measurements at time 3. So there's like some natural time foliation in the sequence of measurements that you make. But the thing is that it had been known for quite a while that for most error correction procedures, that time sequence was not actually very important. In fact, for circuits, if you start with circuits that only involve the Clifford group, which is what you need for most fault-tolerant computations, like error correction procedures with stabilizer codes. So a Clifford group computation, all the measurements can be simultaneous, or they can be in any order. And it doesn't matter. The point is that the measurements that you're making in the measurement-based model don't depend on the previous measurement results, unless you start to deal with non-Clifford group gates. So while the circuit that you started with kind of forced you into this time foliated picture of the measurements, the measurement-based model doesn't care about that. And so Nickerson and Bombin said, well, okay, so what if we, instead of deriving our fault-tolerant circuits from fault-tolerant measurement-based protocols from fault-tolerant circuits, what if we just come up with new ones that take advantage of this property of measurement-based computation and that don't have a natural foliation into time? And so they did that, and they came up with some fault-tolerant protocols that were more robust against loss than the fault-tolerant protocols that were derived from circuits. So it's a little difficult to immediately translate this back to the circuit model, because the notion of time is kind of built in fairly inherently in the circuit model. But I think there's still a lesson that we can draw, even if we're only interested in circuit model computations, which is that we shouldn't just think about space and then think about time as two separate things. We should think about them together. Okay, so when we do that, what do we have? So what we have is we can say, well, we have some circuit, okay? So if we have a fault-tolerant protocol, if somebody gives us a fault-tolerant protocol, and we kind of don't know anything about how it was created, we can just think of it as some sequence of gates, right? And some of those gates are in parallel, some of them are sequential, but we have some procedure in the fault-tolerant protocol to identify where the errors are. And so the thing is that originally, you know, in the old model of fault tolerance, we wanted to say which qubits the errors were on. And by controlling error propagation, we made sure that the errors stayed on those qubits. They might have gone to some different block of the code, but basically we knew where those errors were. Okay, and so it didn't matter exactly when those errors occurred, because they stay in place. And then when we finally get around to identifying where they are, they're still there, we can correct them. Whereas if we allowed error propagation, well, then the errors could spread to additional qubits. And if we don't identify them fast, then that seems like a problem. But if we think of this idea of let's put space and time together, instead of identifying where the errors occur, we want to identify both where and when the errors occur. And so if we have this circuit and we think of it in a space-time picture, we say we want to identify which gates are the ones with errors. And if we can do that, then again, we don't care so much about error propagation because we know how the error propagation will proceed. And so we can undo the effects of the error even if it's propagated to many qubits. So let's do a little calculation to see, if this is even plausible. So suppose we have some error correction circuit, right? So its only job is to correct errors. And it involves n logical qubits, and then the number of physical qubits is going to be n plus m. So we have m additional qubits beyond the kind of the logical qubits that we have, or ones that we're kind of saving for later computation. So it's more than the logical qubits, I guess. So suppose we have this error correction circuit, and we take a piece of it that lets us correct errors, and it has T gates in this piece of the circuit. Now, each of those gates there's multiple different kinds of errors that could occur to it. So there's A possible errors that can occur on each of the gates. So, so you can calculate, we say if the error rate is P, then we kind of expect that there will be P error per gate, or error rate per gate. Then we expect P times T gates to have errors in them within this chunk. And each of those errors, there's A possibilities, and so there's there's T clues, P times T different sets of P times T gates, and then we have A to the PT possibilities of what those different kinds of errors are, and then we have this very long list of possible errors. This is in principle. Obviously, you wouldn't want to write down such a long list, and we say we want to find out which of these long list of possible errors is the one that actually occurred, right? Because that'll tell us which gate went wrong and what kind of error it was. And so to do that, well, we need log of the number of errors, bits of information, at least, right? If we don't get information optimally, it could be more than that. But if you take the log of that, well, then you get this quantity T times H of P plus P log A, where H of P is the binary Hamming entropy, minus P log P minus 1 minus P log 1 minus P. And so in particular, the number of bits of information we want it depends on P, right? If the error rate is low, we don't need so much information. If the error rate P is high, we need more information. That kind of makes sense. But in particular, it's proportional to T, the number of gates in this chunk of circuit that we're trying to correct. And so that means that the number of measurements that we make has to be at least equal to the number of bits of information that we're getting. So M, the extra qubits that we're using to correct errors, has to be at least greater than this amount of bits that we need. And so in particular, if we have a circuit that takes D time steps, it has depth D, then that means that T is going to be D times the total number of qubits we have. And so if we look to bigger and bigger circuits that have larger and larger values of N and M, well, that means that T is already linear in N and M, and so this D has to stay constant. It can't get bigger, because if D got bigger as we made N or M larger, then that means that the number of gates that we would have would increase more than linearly with M, and in particular, the number of bits of information that we need to identify the error would increase more than linearly. But if we can have a fault-tolerant circuit where everything is constant time, then at least in principle, it should be possible to uniquely identify the gate that occurred and what kind of error occurred. Now, there's some complications there. You can't ever distinguish between an error that occurred before the gate and an error that occurred after the gate if the two are related by error propagation. You don't really need to. So, uniquely identifying the errors is maybe asking too much. But, this idea of basically identifying which gate the error occurred in is something that we cannot do with existing fault-tolerant protocols. But it seems like it might be possible in principle. And that's kind of one of the goals of this new method of fault tolerance, is to come up with fault-tolerant protocols that give us more information about when the errors were, as well as where they are, so that we can correct kind of more robustly and deal with a wider variety of protocols. Okay, so so one way to think about these new fault-tolerant protocols is as a sort of space-time code, right? It's still an error-correcting code, right? An error-correcting code, its purpose is to find the location of errors. It's just now we're trying to find the location in space and time, right? So it's a very similar goal. It's just because of the mathematics of space and time, it works a little bit differently than, you know, a regular quantum error-correcting code. So, one thing you might wonder, you know, if we have lots of existing protocols, do they all have this constant depth property? And the answer is no, they don't. Many of them have you know, fault-tolerant error correction procedures that grow quite substantially with the system size. And why should that be possible based on the argument before? And the reason is because, you know, in the old model of fault tolerance, we were not trying to identify what time it did. We used our control of error propagation to say that didn't matter, right? And so actually, when we identify, thinking in this new picture, in the old picture, we identified where the error occurred, but we didn't identify when. So there's many different gates that could have caused this same error. And so the fault-tolerant protocol was designed to be kind of degenerate, right? In the sense that there's many errors that end up doing the same thing to the code. And so that reduced the amount of information we had to get. But at the same time, it restricted the kinds of protocols that we could look at. And so again, if you're thinking in the old picture, then you might look at one of these newer dynamical protocols and say, well, but where's the quantum error correcting code? If you're just doing some sequence of gates, where is the code, right? And it has to be there, right? Because if you stop at some point in time, the data must be encoded in a quantum error correcting code. Otherwise, any errors that occurred at that time would be uncorrectable. And so that's true. If you stop it at any time slice, then the data will be encoded in a quantum error correcting code. But if you stop it at a different time slice, it'll be a different quantum error correcting code. So in a code that's built according to these principles that I've been suggesting to you, the code is changing all the time. It might change in a regular way. It goes in cycles like a Floquet code, or it might change in an irregular way, and maybe you never repeat the same code again. So that brings up an interesting problem, which I'm not completely comfortable with, but is an interesting question to continue to think about, which is, if the code keeps changing, what does it mean to do logical gates? So going back to the idea of code deformation, the advantage of going through a cycle and ending up back where you started is that it's easy to compare the logical state at the beginning of the deformation with the logical state at the end of the deformation. And because it's the same code, you can say, well, before we had this state, now we have this state, therefore the logical state has changed, we've done a logical gate. But if you have two different codes, you know, there's lots of different ways that those codes could be mapped onto each other. And you know, without a kind of principled way of saying what the right one is, it might be kind of ambiguous what the logical gate would be. And I think that's true. And in fact, that's something you can take advantage of. You can say, well, we have these two different codes, and before this was the logical 0 and this was a logical 1. And now in the new code, this other thing is the logical 0 and this other thing is the logical 1. And therefore, the state that was originally, you know, some particular superposition of 0 and 1 is now a different superposition of logical 0 and logical 1. And so we've done a gate. The thing is that you know, in principle, you could just pick your logical 0 and logical 1 in the new code to make it have done any gate that you wanted. You could do the deformation, and it automatically does a gate. And And to a certain extent, that's correct. I think you actually can do that. It's this idea of virtual gates that's already been explored in a more limited context with phase gates. But the thing is that there is a catch, which is that eventually you are going to have to come back to some physical limitation of what kinds of things you can do. So for instance, if you want to make a measurement, right, maybe you can make a measurement that's consistent with certain logical basis states, but not with other choices of logical basis states. And so at that point, you have to assign the logical 0 and the logical 1 to be consistent with the things that you're actually able to measure. And then once you do that, that sets constraints on your ability to do logical gates in this virtual way by kind of redefining the logical basis states. You have to make everything work out with your actual capabilities. And trying to keep everything consistent is the thing that ends up limiting you. And so you have to be careful about how you take advantage of this freedom. Okay. And then the last question, which is a really important one, is how can you use these ideas to build fault-tolerant protocols? And in particular, how to build better fault-tolerant protocols than the ones we have now. And I really don't have a very concrete idea of that at this point. Although I have some additional ideas working with some other students that may help, but they're still in an early stage. So okay, but let me say a little bit about what we do know about these codes. So in particular, one approach, and I'm not certain this is the right approach, for describing these fault-tolerant protocols in this formalism is to come up with a new idea called a space-time code. Actually, it's not new. It dates back to 2017, but it kind of lay on the shelf for a long time until recently. And so in the space-time code formalism, then what you do is you convert a fault-tolerant circuit into a quantum error-correcting code, and in particular into a subsystem code that has gauge operators. And so the physical qubits of the space-time code are labeled by both a time and a location, a qubit location, in the original circuit. And so you have all of these qubits. So you have many, many more qubits in the space-time code than you actually have in the circuit. And then each of the gates, enforces some sort of error propagation in the circuit. And so that's represented in the space-time code by gauge operators. And then you also have some other constraints that have to do with your initial states that you prepare and the measurements that you make. And those contribute to the stabilizer elements of this subsystem code. And then you can show that to a certain extent that the ability of the fault-tolerant protocol to identify faults in different locations in space and time corresponds to the ability of the space-time code to correct errors. So if you can design the space-time codes, then you can get a fault-tolerant protocol. Now that turns out to be rather difficult in practice, but again, I have some ideas towards that. Okay, so then the next thing I'd like to say, let's see how much time I have. Okay, the next thing I'd like to talk about is what are the properties that these dynamical codes can have, and that's important because we have a lot of knowledge about kind of standard static quantum error correcting codes, and we know what things we can do and what things we can't do. But dynamical codes are different, and they might not follow those constraints. And so you might be able to do some stuff with dynamical codes that we could not do in other ways. And so this is the work from the paper with Xiaozhen. And so in particular, let's define a dynamical code as a sequence of stabilizer codes. So obviously you could look at non-stabilizer dynamical codes, but we haven't done that. So if we have this sequence of stabilizer codes, then what we can do is we can talk about the ISP, the instantaneous stabilizer group of the code at any given time, right? And so we start out with some code C1, and then we update it using gates or measurements to get to some code C2, and then to code C3, and then code C4, and so on. And then maybe it cycles like a flow K code. So after C4, we go back to C1, or maybe it doesn't repeat. And so one challenge in this type of code is that in the flow K code, you see it has this weird property that instead of taking your code and measuring the error syndrome, instead you have some new measurements that kind of update the code and at the same time gather information about errors. But in order to actually figure out the error syndrome of this code, you have to combine your measurement results from different time steps. And so this is a property that makes the whole notion of error correction a bit more subtle. And so the thing that we were studying was, how does that information accumulate? How do we learn the syndrome information if it's spread out over multiple time steps? And so the idea is that in this particular model, we're just updating by making measurements. And then each measurement we do gives us some information which may or may not contribute to learning, to teaching us the error syndrome, and therefore identifying any errors that have occurred. So, so one concept that turns out to be important is the notion of masking stabilizer generators. So in particular, we have some. So the ISG has a bunch of stabilizer elements, and we have to measure the eigenvalues of these stabilizer elements to find the error syndrome and to identify the errors. And so some stabilizers are unmasked. We measure them directly, or measure them, through a sequence of pieces that we put together to learn that syndrome. But at any given point, there may be some other stabilizer generators that we haven't learned the eigenvalue for them. And so while those were still constraints, at least initially, they might have been gone by now. Those are constraints on the code. We don't know the value of the error syndrome. So those syndrome bits are masked. And then we can further subdivide the masked generators into temporarily masked generators and permanently masked generators. So a temporarily masked generator is one where we haven't yet measured the eigenvalue of it, but we will in the future. And then permanently masked generators are ones where we will never measure that value. And so it might be that we're never measuring the eigenvalue of that generator because it's not possible, right? If we make a measurement and the old stabilizer generator was incompatible with the measurement that we made, then we've kind of erased the eigenvalue. It's gone. There's no information about it left in the state anymore. So we can never get that syndrome information out, that particular piece of it. Or it might be because we just, do other stuff and we never get around to measuring it. That's a possibility too. So, but the distinction between temporarily masked and permanently masked can be important because when we start to plan ahead what we're going to do in the future, it's important to know which things are already kicked out, already impossible to measure. Okay, and so the thing is that if you're in one of these intermediate states where you've measured some of the generators and not others, then your ability to correct errors is less than what you'd have if you had measured the full error syndrome. So instead of the regular distance of the code, you can define an unmasked distance, which kind of uses the syndrome information from the unmasked generators, and maybe there's some ambiguity in the error that we can tolerate because it doesn't affect the logical errors. But the point is that that's potentially more limited than the full distance of the code that we could get if we were able somehow to measure everything. And as you proceed along the dynamical evolution of this code, and you unmask more and more generators, this unmasked distance can increase, right? So the distance is a sort of a changing thing in time. It starts out, you have very little ability to correct errors. As you get more and more information, you get more and more ability to correct errors. So that makes sense, right? And so again, the question is, how long does it take to get this information, and how do we know which information we can acquire given a particular protocol? And so it turns out it's actually quite subtle to identify which generators are permanently masked and which ones are unmasked. I mean, there's a nice algorithm to do that, which I'll not go through in detail, but flash at you in a little bit. But let me show you an example so you can see that even very small changes in the protocols can change you from one type of masking to another type, or remove it altogether. So there's going to be two examples, and they start in the same place. So in these examples, we start with the generators XXX and ZZI. And so the state is an eigenstate of XXX, and it's an eigenstate of ZZI. So we'll assume it's a +1 eigenstate of ZZI, and it's an eigenstate with eigenvalue -1 to the A of XXX. And we want to know what A is. So in the first example, well, in both the first and the second example, the first thing we do is we measure X on the first qubit. Why are we doing that? Well, that's part of the protocol that was given to us, okay? And so we get some answer. We get the answer B. So the eigenvalue of XII is -1 to the B. And so the thing is that XII doesn't commute with ZZI. So ZZI is no longer in the stabilizer. It's no longer, the state is no longer +1 eigenstate of ZZI. Instead, it's an eigenstate of -1 to the B XII. And so that's true in both examples. And so now in example 1, the next thing we measure is ZII. So we measure Z on the first qubit. Now Z on the first qubit doesn't commute with X on the first qubit. So we're going to kick that out. That's no longer, XII is no longer in the stabilizer. And it also doesn't commute with XXX. So we're also kicking out XXX. But it does commute with the product of those two things. So -1 to the A XXX times -1 to the B XII, that's all. The product is also in the stabilizer, and it commutes with ZII. So that product -1 to the A plus B times IXX is in the stabilizer still after this measurement. Okay, and then if we were to measure that, well, we'll learn A plus B by finding out the eigenvalue of IXX. And since we already knew B because we did that measurement before, well, we can deduce what A was. Okay, and so in the first example here, XXX is now an unmasked generator. We've learned its eigenvalue. But now let's look at example 2. So example 2, remember, starts the same way. We measure XII. But at the second step, instead of measuring Z on the first qubit, we measure Z on the second qubit. Doesn't seem like it should be a big difference. Z on the second qubit still kicks out XXX, right? It still anti-commutes with XXX. But now it commutes with XII. And so now the stabilizer is -1 to the C IZI, if the result of that measurement was C, and -1 to the B XII. And you'll notice that there's no A in there anymore. So no measurement you make now is going to tell you what A is. So in this version, XXX is now a permanently masked generator. We can never find out its eigenvalue. So this one small difference of measuring Z on the second qubit instead of the first qubit made the difference between unmasking XXX, making it possible to learn its eigenvalue, versus permanently masking it. And you see, even in the first case, we kicked XXX out of the stabilizer, but the information was still there. So these things, like I said, can be pretty subtle. Okay. And so in order to deal with this, we came up with an algorithm to track how masking works. I don't want to go through the details, but the basic idea is you start with your initial stabilizer S0, and then you keep track of two sets. So one of them are kind of evolutions of the original generators in the original stabilizer, the ones that you're trying to find the error synchrome for. And another one is extra information that's available for measurements. And then whenever you make a new measurement, there's 4 possibilities depending on whether that measurement commutes with both of those sets or commutes with only one of them. So that's 2 possibilities: commutes with C but not V, commutes with V but not C, or commutes with both of them. And then we have an update rule based on the usual kind of stabilizer formalism that tells us how to update C and V based on these 4 cases, depending on what measurement we did. And in particular, the case 2, where M commutes with everything in V, but doesn't commute with C, is the case where we end up with permanently masked generators, because we end up kicking something out of the set that can no longer be learned. And then at the end, we have these two sets C and V. We look at the groups generated by them and look at their intersection. So those are the things, it turns out, that have been unmasked, where we have the information needed to deduce what their error synchron was. And anything that was kicked out, that's permanently masked. And then finally, anything that doesn't fit in either of those categories. So it's not in C intersect V, but it's still in the set C, that's temporarily masked. So in particular, some future measurement we make, it could still learn that eigenvalue. Okay, so so then once you have this notion of understanding of how the error synchrons get revealed and permanently masked, you can start to ask other questions about these dynamical codes. And so, for instance, here's some facts we discovered about Floquet codes. So, for instance, you can say, suppose we start with some just kind of random state, or maybe the all zero state, and we make a series of measurements of a Floquet code. Well, it makes sense that eventually it should equilibrate into the same code space, right? Into some particular code space, and we just keep on cycling those sequence of codes, right? Floquet code is the case where we cycle between a bounded set of codes. So it turns out that what happens, and you can show it using our algorithm, is that every time you repeat your cycle, you can add generators to the ISG, but you can't subtract generators. And so the generators from the last round are still there. If you're in the corresponding place, those generators can get kicked out later in the cycle, but then they get replaced and they come back. And so every time you go around, you get to the same code, same kind of place in your cycle again, the same measurements. And the generators that were in the ISG before are still there, but you might have some more things. And so what that tells us is that, and furthermore, it turns out that if you stop adding generators, so if you have one cycle where the number of generators is the same, then that means you stabilized. And so what that means is that there's a maximum number of cycles that you could use. So the maximum size of an ISG is the number of qubits in your system, number of physical qubits. And so every cycle, you could be adding one generator, but you have to stop once you've reached n generators when you have n qubits. And so the number of cycles that you have to do is at most equal to the number of qubits in the system. But we found examples where it actually takes that long. So it's not just 1 or 2 cycles. It can be many, many cycles. And when n is very large, it could be linear in n number of cycles. So it can take really a long time to reach kind of equilibrium, albeit not exponentially long. Then you can say, well, okay, so once we've reached this equilibrium, once we have this code, now suppose there's some errors and we want to measure the error synchrone. How long is it going to take to unmask everything that's going to be unmasked, right? When are we going to learn the error synchrone? Well, it turns out it can also take a long time. It can take as many, in fact, it does take exactly as long as it takes to initialize the code in the first place. So if it took n cycles to initialize the code, it takes n cycles to learn the error synchrone. And I should say that this ability to have very long initialization times and synchron measurement times, that holds even for geometrically local codes, right? So it's just a kind of general property about these dynamical codes that they don't have to, it can be quick, but it can take a long time to learn the error synchrone. Okay, so that's most of what I wanted to say. So I guess to summarize, I think these dynamical codes are a very interesting and promising way to approach the problem of fault tolerance. And so we're still kind of feeling out the properties of them. They seem to behave very differently from regular quantum error correcting codes. And we have limited ability to construct and manipulate these protocols, but we're kind of learning more about them all the time. And so I think they have this potential to give us protocols that don't look at all like our existing fault-tolerant protocols. And, you know, some of those protocols will be lousy, of course. Most of them will be lousy, but maybe some of them are really good. So my hope is that, you know, further research on them will help us come up with new protocols that will push the frontiers of quantum computation even further. Thanks.
Thanks a lot. We have time for questions. If you have a question, raise your hand. Same as for the online audience. So actually, I had a question, if I may. First of all, thanks for this very insightful talk. This was a really interesting overview. You mentioned earlier that I can think of changing basically my code as basically as I go deeper in the circuit as actually doing the gates. Is it clear that for any given circuit, no matter how complicated, it's easy to find what code is the next, and is the choice unique?
Right. So I mean, this is one of the things that I think is not really understood. So far, basically all the work has been done from the standpoint of, you know, somebody has come up with a protocol and given it to you, and it said, and they say, okay, you're going to do these gates, you're going to do this sequence of measurements. And if you have those, and these are all stabilizer, all these examples are stabilizer codes. And so if you have that, I mean, it's easy to analyze and say, oh, well, if we make this measurement, the new code is going to be this. But you'd really like to go beyond that, right, in order to design protocols in some sort of more principled way. And you might have a situation where, you know, what code you want to do, you know, what measurements you want to do depends on the results of past measurements, right? You might say, oh, this is the error. I should make some measurements that are going to help me learn what that error is. And that, in principle, could kind of bifurcate. Instead of going for some particular path of codes that's always the same path, it could bifurcate, and you could go to very different codes depending on the results of your measurements. And it's not at all clear how one would design or manage such protocols, because they could get pretty complicated pretty fast.
But it's not a priori clear that this works at all, because it could be exponentially hard, say, doing it on live while you're doing the computation.
Right. I mean, so certainly finding, you know, okay, so even for regular error correcting code, if you take an arbitrary quantum code, finding kind of the optimal decoding given the error syndrome is already a hard problem, right? I mean, it's NP hard. If you kind of maximum likelihood error, if you want to get the exactly most likely error, that's sharp P hard in a stabilizer code. So trying to do the optimal thing for an arbitrary code, that's definitely going to be a hard problem. But how do we get around that with error correcting codes? Well, we work with special codes that have an easy decoding problem. And so presumably we want to do something similar with dynamical codes, that we have a special family of dynamical codes where making decisions is much easier. But again, I have no real idea how to find or design such protocol.
Do we have more questions? Perhaps from the online audience. We don't have any more questions. We'll stop the recording and we'll speak again.